example, a conical tank is being filled with a chemical at a rate of 2 feet cubed per minute. The tank has a top radius of 5 feet and height 12 feet. How fast is the chemical level rising when the level is 4 feet high? And here the volume of a cone is given. It's pi r squared h over 3. So first we can make a sketch of the conical tank. You can see the top radius of the tank is 5 feet and the height of it is 12 feet. Since the tank is being filled with chemical, the volume of the chemical is changing, and the radius and height of the chemical in the tank is also changing. In this case, the volume, radius, and height of the chemical in the tank is changing with respect to time. We want to find how fast the chemical level is rising when the level is 4 feet high. So we want to find dHdt when h is 4 feet and dV/dt is given in the problem as 2 feet cubed per minute. And the relation between the changing variables is given by the volume of the cone that's given. From the problem, we have the rate of change of v and the rate of change of h, but we have no information on the rate of change of r. Looking at the picture of the tank, you can see that the two right triangles will be similar triangles. So we have no information on dr/dt, but we can eliminate r using similar triangles. Because there are similar triangles, the ratio of the corresponding sides will be equal. So in this picture, r over h will be equal to 5 over 12. So we can use this to rewrite r. R will be 5h over 12. So now we have a relation between only v and h, so we'll just simplify. On top, I will distribute the square to all the terms in the bracket, and then to divide by 3, I will multiply by the reciprocal 1/3. H squared times h will be h cubed over 144 times 3. So v will be equal to 25 pi h cubed over 432. So we will take the derivative of both sides with respect to t. So on the left we have dV/dt is equal to 25 pi over 432 is just a constant, so we can keep it in the front. And the derivative of h cubed is 3h squared dH/dt. So now that we've taken the derivative, we can plug in the values of the moment. dV/dt is 2 and h is 4. Also 432 from before was 3 times 144, so the 3 in the top and bottom can cancel. To isolate dH/dt, we'll just divide both sides by 400 pi over 144, or multiply both sides by the reciprocal. So 2 times the reciprocal 144 over 400 pi will be equal to dH/dt. This will be equal to 288 over 400 pi. If we reduce the fraction, there's a common factor of 16 in the top and bottom that you can cancel. And the rate of change of h is 18 over 25 pi feet per minute. In the next example, a camera on the ground is filming a space shuttle liftoff. The shuttle rises with position function s of t in feet, where t is in seconds. The camera is 2,050 feet from the launch pad. Find the rate of change in the angle of elevation of the camera when t is 10 seconds. So here in the picture we can see the camera is 2,050 feet away from the launch pad. The shuttle is rising above the launch pad with height s. S is changing with respect to time, and also the angle of elevation of the camera is also changing with respect to time. So here, both s and theta are functions of time. We want to find the rate of change in the angle of elevation of the camera, so we'll want to find d theta dt when t is 10 seconds. From the question, s of t is 52t squared, so we can calculate ds dt. It will be 52 times the derivative of t squared, which is 2t, so it will be 104t. ds dt when t is 10 seconds will be 104 times 10, is 1,040 feet per second. And we can also calculate the height s when t is 10 seconds. S of 10 will be 52 times 10 squared, which is 5,200 feet. So even though in the picture we have a right triangle, we won't use Pythagorean theorem for the relation, because we want to relate the height s with the angle theta. We can relate the angle theta and the opposite side s and the adjacent side 2,050 using tan theta is equal to opposite over adjacent, or tan theta is equal to s over 2,050. So that is the relation we'll take the derivative of implicitly with respect to time. So the derivative of tan theta will be secant squared theta. Theta is a function of time, so we multiply by d theta dt. 1 over 2,050 is a constant, so we'll keep it. The derivative of s is 1, and since s is a function of time, we'll have ds dt. So we want to find the theta dt, so I will divide both sides by secant squared. So just a note on the side, since most people don't have a secant button on their calculator, we can use that cosine theta is equal to 1 over secant theta. If you square both sides, cosine squared theta will be equal to 1 over secant squared theta. So from before, ds dt was 1040 feet, and to find the value for cosine squared theta, we'll need to find the value of theta at t is equal to 10 seconds. So we'll use the original relation to find theta. We know that tan theta is s over 2050. When t is 10, we calculated that s was 5200. Then theta will be arctan, or tan inverse, of 5200 over 2050. So here we get 1.2 radians. So now we can calculate d theta dt. It will be 1040 times cosine of 1.2 radians squared over 2050. So here we get 0.067 radians per second. So just a note to always keep your calculator in the radian mode for your calculation, because the derivatives of the trig functions are not the same when you don't use radians. The following related rates problem is from Richard Shoemaker, who taught physics and astrophysics at Dawson College. It is about the star of our solar system, the Sun. In the 19th century, people knew that the Sun was a hot ball of gas of radius 7 times 10 to the 8 meters, with mass 2 times 10 to the 30 kilograms, and that it emitted about 4 times 10 to the 26 joules per second. The question was, what is the source of this energy? One idea was gravitational contraction. For a uniform density sphere, the gravitational potential energy U is given by this formula, minus 3 over 5 gm squared over r, where g is a constant. This formula is derived in another video. If the Sun contracts due to its own gravity, the radius r will decrease, and this makes U more negative, releasing energy. The Sun emits 4 times 10 to the 26 joules per second, and another 4 times 10 to the 26 joules per second goes into raising the Sun's temperature. So combined, du dt is equal to minus 8 times 10 to the 26 joules per second. So the question was, how fast does the radius of the Sun r need to decrease in order to release 8 times 10 to the 26 joules per second? Both u and r are functions of time. And the question is to find dr dt, given that du dt is minus 8 times 10 to the 26 joules per second, and the relation between u and r is given by this formula. So we'll take the derivative implicitly with respect to time of both sides. On the left, we have du dt. On the right, minus 3 over 5 gm squared is a constant, so we'll keep it in the front. And then we'll take the derivative of r to the negative 1. It will be negative 1 r to the minus 2 dr dt. So here we can simplify negative will be positive, and r to the minus 2, I'll bring it in the denominator. When we want to isolate dr dt, we'll just multiply by the reciprocal. 5r squared over 3gm squared du dt will be dr dt. So after plugging in the values for r, gm, and du dt, we find that dr dt is minus 2.4 times 10 to the minus 6 meters per second. So incredibly, the Sun would only have to contract by minus 76 meters per year. Since the Sun's radius is 7 times 10 to the 8 meters, it could keep this process up for millions of years. And in the 19th century, gravitational contraction was thought to be the source of the Sun's radiation. Now we know that the Earth and Sun are billions of years old, and nuclear fusion is what powers the Sun. However, gravitational contraction still plays important roles in the life of a star. For example, gravitational contraction is the source of heat needed to start nuclear fusion in newly forming stars, and it's also the source of much of the energy released in a core collapse supernova.